Okay, in this example, they said estimate e to the 1.45 power using a Taylor polynomial about x equals 2. What's the least degree of the polynomial that assures an error smaller than 0.001? Okay, so some things we need to be able to draw out of this one. One, if this is what we want to estimate, the equation that we're using for this one would be e to some power. So that's the function we're looking at. Like other problems, we know we're going to need to find some derivatives of this because our error here to whatever number we're looking for should be less than or equal to absolute value of that m value over n plus 1 factorial, and then we got x minus whatever that value is. We'll call it c. I think we saw it in some other ones, to the n plus 1 power. And so we're going to need some different derivatives of m because we know m in these problems is the n plus 1 derivative at the biggest value. So what is the derivatives of e to the x? Well, we kind of have a nice function here because first derivative is e to the x. Second derivative is e to the x. In fact, any derivative here is going to be e to the x. It doesn't matter what we put in there, every derivative is e to the x. So that's helpful for us. So let's see what we can fill in on this problem then. So what we're looking for is what is that r value here, and we know what we're looking to find it at. We're trying to find r to some degree here at the number 1.45. The problem is, what's different is what is that number of terms? That's different in this one. So we're going to have to try to fill in what we know about this other stuff first. Let's start with this m value because I think we can find that. We know any derivative of this is going to end up being e to the x. And so what is the, and I'm going to put z here for now. What is the number z on the interval from 2 here to 1.5? What's going to be the biggest value for that? Well, e to the x or e to the z, however you want to think about it, if we graph that one, we know that what that graph looks like. That's a exponential graph. It's going to keep getting bigger and bigger for the bigger x values you put in there. So 2 is definitely going to give us a bigger value than 1.45. So this is going to end up being e squared. Okay, so e squared is our m value. We don't know what n is. This is different from other problems. So we're going to leave this for now as n plus 1 factorial. We do know what our value is here. We're centering it around 2. So this is going to be x minus 2. And again, we don't know what n is here. So n plus 1 power. But we do know that we want all this error to come out to be less than, try that again. We do know that we want it to all come out to be less than this value here of 0.001. And so we're going to try and solve and see what would give us that. So the only constant we have in this whole Lagrange error here is that e squared. So what we could do here is let's divide by e squared and get that at least out of this. So we're going to divide that. So now we know our error here. And I'm going to try and separate this out here a little bit. So we don't know the value of n. But we know the stuff left in this absolute value here, x minus 2 to the n plus 1 power over n plus 1 factorial. We want it to be less than or equal to 0.001, but we're going to divide by that e squared to get that value out. So on your calculator, let's do that. So let's say 0.001, and we're going to divide by e squared. And if we do that, now we know it should be less than this. And that's scientific notation to the -4 power. So we'd want to move that decimal point to the left 4 times, which means there's going to be 3 zeros in front of this number. So it's going to be 0, 0, 0, and then 135 was the number we had up there. So in order for this to work, we need whatever that n value to give us a value less than that. So what we're going to do now is there's a little bit of guess and check here. We're going to have to try to plug some values for n in and see which one is going to give us our value that we want here. So let's make a little table. We're going to try some n values out here, and we're going to plug that n value in. Oh, I guess there's one other thing we can plug in here, sorry. We do know our x value. Our x value is the 1.45. So we can plug that in, 1.45. And so if we subtract 1.45 minus 2, that's going to come out to be, should be negative 0.55. So we're going to try to figure out what does that n value have to be that's going to give us the biggest number here. So we got this as our function. All right, so what value of n is going to give us something that's less than what we got in there to ensure that we're in the best place possible here. So let's, I don't know that 1 or 2 maybe is, let's try 3 to start, and we'll work from there. So what if we were to put 3 in for n? What kind of value are we going to get here? So we're going to put this function in, and we want to take the absolute value of it. So I'm going to do math, go over absolute value of, and then I'm going to create a fraction here with our numerator denominator. So we got negative 0.55 to the power of, we're going to put in 3 here. So if we put in 3, 3 plus 1 is going to end up being power of 4. And then on the bottom, if we put 3 and 3 plus 1 is 4. So 4, and then factorials under this probability menu. Put that in there. All right, so let's see what this gives us. So here, this would ensure that we are 0.0038. That's not as small as we want it to be here. We want it smaller. So let's go up a number. Let's try 4 now. What if we were to put 4 in? So we're going to do same thing. And to shortcut this, I'm going to go back up, copy and paste that. Let's just go back now and change these 4s to 5s, because that's what we get if we put n of 4 in there. All right, so I'll change this to a 5. This comes out to be, now this is scientific notation, to the -4th power. So I got to move that decimal point over 4 times to the left, putting 4 zeros in front of that number. So this is going to be 0.1230419. Is that smaller than our value there? No, it's slightly bigger. 0.004 is bigger than 0.0001. So I think the next one should give it to us. Let's just check here. What if we put 5 in? So I'm going to copy and paste that again. Now let's change those to 6s, because 6 would be our number if we put n equals 5 in there, because it's n plus 1. So change these to 6. Yes, now that one, if we got that scientific notation number to the negative 5 power, we want to move the decimal point over 5 times, putting 4 zeros after the decimal. So it'd be 0.0000, what was that, 384. This number is now smaller than the one indicated. So n equals 5 is the degree we'd want that polynomial. So to answer our question now on this one, if we're going to write out our answer, we would want the degree of the Taylor polynomial to be at least 5 to assure that our error here is smaller than 0.001. So that's how we would answer the question. All right, there's one more of these. I want you to try to pause and try this one on your own and see what you get. All right, let's see what you got. Hopefully you've had a chance to try that. Here you can see that our function is sine of x. So derivatives of that would be like cosine and the negative sine and the negative sine and so on. So it's the nth derivative is going to be plus or minus some variation of sine or cosine. Well, knowing what those two graphs look like here, what is the most and least that value could be? Well, the most it could ever get is 1. The least is negative 1. So the biggest value of the n plus 1 derivative on either sine or cosine is going to come out to be plus or minus 1, which the absolute value of that's going to be 1. So our m value for our Lagrange error here is going to be 1. We know it's a Maclaurin one, so that tells us our value here is going to be centered at 0. And then we're trying to find it at 0.4. So 0.4 is our number we're putting in there. So if we simplify that, we end up getting that this Lagrange needs to be less than 0.001. So now I made a little table here and plugged them in my calculator, looking at the values I got till we get something less than 0.001. That's bigger than 0.001. This one is still much bigger. This one got close, 0.001, but then 0.6, which is slightly bigger still than what we got here. So it looks like we're going to have to go to the 4th degree in order to get this. So answer would be that we would want a Taylor polynomial to the 4th degree centered at that to make sure our error is less than 0.001 when estimating 0.4 on that one.